It will be a bad picture. Okay, thank you. I'll be talking about displacement current in ferroelectrics and about recent experiments about this topic. So outline includes first some theory, and then I will give you 3 examples. These are not all examples we have considered, but just, you know, I have no time enough to show all of them. So I will talk first about PZT domains, switching and emergence of displacement current during such switching, and then BF4, and finally PMN, lead magnesium niobate relaxer, ferroelectric relaxer. So I start from general theory, which we introduced in 2013, and we started from general formula for magnetization, but here you see only part of current. This is displacement current, which is dP over dt, and this is why I will talk about dynamical magnetization rather than about total magnetization. Dynamical magnetization, when we plug for displacement current, this formula is expressed by this integral, and then if the structure is constant, we can take derivative over time with respect to time out of the integral, and under the integral we have exactly ferroelectric toroidal moment. So finally we reduced dynamical magnetization to time derivative of ferroelectric toroidal moment, or this is minus I omega times the toroidal moment. And magnetoelectric susceptibility corresponding to these dynamics is given by the derivative of time derivative of ferroelectric toroidal moment with respect to electric field. So another theory was presented by Zelashinsky and Mills, but this is kind of Landau type theory, so it's not exact, but just approximate. And first experiment was done in group by Florova in 1988, and they did find a magnetic moment when they switched polarization in ferroelectric domains. So here your first example of PZT, and you see thin film, and this is one domain with up spins, sorry, not spins, displacement, polarization. And the other domain with down spin displacement. This ferroelectric conference is not ferroelectric, and that's why it's mess of magnetic stuff with spins and polarization. And here you see closer domains, which are Landau type domains. And this one looks to the right, this to the left, and finally we have a vortex if we place the origin of the coordinates at the middle of this picture. In this case, toroidal moment is finite and maximum with this choice of the origin. Then we applied electric field up, and the up domain widens and the down domain shrinks. So if we calculate toroidal moment in such a situation, I should note that before we should subtract the constant polarization, because otherwise it will be a mistake. And the remaining toroidal moment becomes smaller, so it's decreasing. And this means that we already have emergence of magnetization in such a system. So here I just showed dp over dt at each site, how the local mode changes at each site, and you see that here the arrows are very large and up, but here they are down and small. So the part where they are large, this is the domain wall, which is moving. And this is why dp over dt here is maximum. Here, the biggest errors are down, which means that the domain wall moves back. So we have correspondingly curl of electric current, and this means that we have magnetization in one direction here and in the opposite direction in the right slide. Here you see the plot of magnetization versus time. So we have spike down, then up after switching, down, up, etc. Okay, this is first example. Then I will talk about a recent experiment by Wu and others, which showed one of the first measurements of displacement current in hexagonal rare earth mongonites. And they applied gigahertz frequency by using a chip, so at a particular point, and they found that current increasing with frequency practically so very strongly, and gigahertz are somewhere here. So this is the current, the largest one corresponding to gigahertz frequencies. The next slide shows calculations performed in the same study. This is calculation done by Sergey Artyukhin. And what he did, he presented a model for rare earth mongonites, and by using that model, he calculated dynamical matrix and found all modes in this system. And there is breathing type mode, which are relatively high frequency, but look here, there is a very low frequency mode, which he called sliding mode, which corresponds to sliding of the domain wall. Here, a study by Irka and others in the same year, 2017, and they constructed by using shell model calculations also dynamical matrix. They found phonons, and again you see that besides normal phonons in this area, they found very low frequency phonons, which they called phazon-like modes. And the lowest frequency was at 0.3 terahertz, so 300 gigahertz. So what we did, we used effective Hamiltonian method, like in the previous example, and we considered two types of domains, 109 and 71 degree domain in BF4, and construction of those domains were in line with very well-known Diego's and others study shown here. And then we applied periodic electric field to this system. So the field was at 2.5 gigahertz and temperature was 10 K. The results were published in this NPG Computational Materials journal. So this is 109 degree domain. This is a projection of the local modes for ZX direction. And this is just a sketch for three-dimensional structure, you see that domain wall is in 1, 0, 0 direction for this type of domains. This is 71-degree domain, also projection to ZX plane. And the three-dimensional picture shows that domain walls here are along 1, 1, 0 direction. So by using these supercells, we calculated the displacement current, dp over dt, versus time. And we fitted these results by harmonic oscillator. So harmonic oscillator has magnitudes and phases. So magnitudes are shown in the upper slides, and phases are here at the bottom. So you see that magnitude at some points, I did not say, these numbers are the indexes of layers. So we calculated these displacements for each atomic layer in parallel with domain wall. And we have first layer, second, and until 24th. So the displacement is large only at particular points, not everywhere. And these particular points coincides exactly with the position of the domain wall. So the response to external electric field is the largest at the domain wall. This is true for 109-degree domains, and direction of that displacement is in the domain wall so that polarization can increase or decrease, total polarization. And for 71-degree, we have the same qualitatively, but as soon as these domain walls are wider, the magnitudes are a little bit lower than in 109-degree case. The phases are very close to pi over 2, which is not surprising. Pi over 2 with respect to the phase of the electric field, which is not surprising because this is displacement current, which is derivative of polarization with respect to time. So the polarization itself should follow electric field, but derivative should be shifted by pi over 2. Here, we calculated dielectric response for each atomic layer in parallel with the domain wall. And what we found that the very large dielectric susceptibility shows up just at the position of the domain wall, but it is much smaller at other positions, while, of course, it is finite at all positions. And here I show example of the response for some position, some atomic layer which is inside the domain wall. And this is imaginary part of response. And here you see some lines, responses which correspond to normal phonons of about a little bit more than 100 and more than 200 inverse centimeters. But this peak is absolutely new one, and it is related to vibrations of the atoms inside the domain wall. So these atoms, these phonons, two-dimensional phonons actually in the domain wall, they are very extremely soft, and so it's about 25 maybe inverse centimeters for 71-degree. And this is in line with Irkach-Linker and others' results. For 109-degree domain, qualitatively we found the same, but also there is additional vibrations corresponding to inside the domain wall atoms, but it is a little bit harder, of about 50 inverse centimeters. So here we estimated corresponding current in magnitude. So this is current density, then estimated width of the domain wall. And by using this, we found that AC current is of about 8 nanoampere, which is measurable. And this is exactly number which was found by, for example, Maximovich by using PFM at kilohertz frequency, but that current was related to impurities, to charges, as we believe. Because according to our calculations, at kilohertz, you cannot obtain such large current, okay, it's not large, but such a current. Because the current, as I showed at the beginning, is proportional to omega, to frequency. So if we found this at gigahertz, then at kilohertz it should be 6 orders lower. And also what is important is magnitude of the field. We used to use a pretty large electric field to see this effect, 10 to 7 volt per meter. And I think that one should use thin films, ultra thin films, in order to have large magnitudes of the fields, and the frequency should be at gigahertz. In this case, the displacement current, as we see, should be seen in experiment. And I believe that experiment which I started with, they also explain their results by displacement current. This is from group by Cheong. Now let's switch to last example, lead magnesium niobate. So here you see what we found for the, so we consider ferroelectric phase of lead magnesium niobate. And we apply field opposite to the polarization. This is just DC field. And we don't have any ramping here in this calculation. And then for different magnitudes of the field, you see the dependence of local mode or polarization on time. The red lines, these are points, but the red lines are fits by nucleation limited switching model. And you see that the fit is pretty good. Here we calculated the distribution of relaxation times. And you see that for small fields it is pretty large. And it is very important for NLS model, because NLS model explains these curves by the wide distribution of switching and switching times. And this is what we found. And only for very large electric fields, extremely large, 2 times 10 to 8, we have narrower distribution. Here we calculated infinite percolation cluster strengths versus time. What happening versus time, the strength decreasing, then vanishes, then stays vanished, and after some time starts increasing and reaches previous value. And the same is true for other magnitudes of the field. Here the local modes in infinite cluster versus time, we see that they stay constant practically. So no switching inside infinite cluster. But then after vanishing, new infinite cluster has opposite sign of the local modes. But note that it vanished, so, and here the strength is close to 0, and then it is increasing, so polarization is the strength times this average local mode. And this is small percolation clusters. They increase in size with time, and these times are where the infinite cluster vanished, and the small percolation clusters are maximum, and then they are decreasing in time after infinite cluster started growing again. Here, magnitude of the local modes, it stays more or less constant, average magnitude. So how can it happen? Polarization did not switch, but local modes are having finite and constant magnitude. What's going on? Here, cosine theta for small percolation cluster, a red line shows average cosine theta of polarization, I mean. And you see it decreasing and then becomes negative. But points show the same, but for separated points, sites in the supercell. And you see that we have very wide distribution of cosine theta. So this small cluster gradually rotate polarization, but infinite cluster doesn't. Finally, the picture is the following. Infinite percolation cluster with time is melting. Small clusters separated from the infinite cluster can rotate polarization, and when infinite cluster vanishes, small cluster continue rotating polarization because only small clusters exist in this interval where infinite cluster is absent. And then these small clusters which finished rotation of polarization merge in new infinite cluster with opposite direction of polarization, which is growing with time. So this is our model, but it can be fitted by NLS model, which is more general, but doesn't have any information about microscopic things which are happening during the switching. Now I want finally, this is final slide, to speculate, can we somehow relate what we have found to displacement current? Okay, we have polarization up, electric field down, polarization rotates. So each side which is rotating polarization does have displacement current, but we found that the angles, not theta, but how you call it, phi or alpha, so in plane angle. So distribution of this angle is homogeneous. So in this means that displacement currents stemming from different rotations compensate each other. And in total it is absent because of symmetry. But imagine that we apply magnetic field perpendicular to electric field. Then the part of these circles of electric current will be influenced by this magnetic field, and in this way we can influence switching. I don't know what will happen, but just we can. And last example, if polarization is up, but imagine that electric field is perpendicular, then polarization mostly will rotate to the left. which means that displacement current in this case, we expect it finite. So we will have magnetic field. Okay, so displacement current, magnetization, magnetoelectric susceptibility, and soft local modes at the center of ferroelectric domain wall can be measurable in ultra-thin films at high frequency, gigahertz, and in ultra-thin films. Thank you.
Okay, we have time for questions.